kind of saw this rule already. It's not a crazy rule. It's just if you are adding or subtracting more than one function, you can take the derivative and use the derivative rule separately on each one. So if I have a function f of x and a function g of x, then my derivative would be the derivative of f of x and the derivative of g of x. So what this means is that if you have a huge polynomial, like we do in A, we can just do the derivative rule for each one separately. So in A, if I was figuring out the derivative of just 3x to the 5, can you see the 5 would come out, hit the 3, give you 15, subtract 1 from the exponent, 15x to the 4th. And then you get to your 2x to the 4th. The 4 would come out in front and give you 8, and subtract 1 from the exponent, 8x cubed. Then we go to the negative 7x squared. The 2 would come out in front, multiply by the 7, give us negative 14x, subtract 1 from the exponent. I wouldn't have to write a little 1 there, because I just have an x that's left. Then the x, what would happen with an x? It just becomes 1. I mean, you could think of it like this, right? The 1 would come out in front, hit the 1, give you the 1. Subtract 1 from the exponent would give you x to the 0. So if you have something that's just an x, it just becomes the number in front. This is worth thinking about also from a graphical perspective. If I had the graph of just y equals x, can you see that that would just be a straight line? And can you see that all the tangents are identical to that line, no matter where you put it? If I draw a tangent at this point, touching only that point, it would be exactly the same. And so if the derivative finds the slope of a tangent, and all the tangents are exactly the same slope as the original line, does it make sense that lines, the slope is the slope? The derivative is the slope of the line. If I had 5x, then the derivative would just be 5. And then, do we remember what the derivative of a constant is? What's the derivative of negative 5? Again, as a graph, that's a straight line. What's the slope of that straight line? It's 0. So you wouldn't have to write that plus 0 if you didn't want to. But sometimes the easy ones are hard at the beginning. So the derivative of a constant is 0. The derivative of just an x would just be its slope. But all the other ones are, well, they're all following the power rule. But there's our answer for something large. Okay? Put this into perspective. Here's our definition of our derivative. Can you imagine plugging in x plus h for every x, expanding completely? How long that would take with the definition? That would take a very long time. And look how quick we were able to do it. Sometimes, like in part B, you have to do some preliminary work. Like, I can't take the derivative of x with a square root, but if I change it to a half, I could. I can't take the derivative of negative 5 over x cubed, but if I change it to x to the negative 3, I could. So sometimes when we're finding the derivative using our rules, we first of all have to be creative to put it in a form that our rules work. So now our rules work. So my derivative, and I'll try to use all the different notations of derivatives so you get used to them better. So the derivative, dy dx, the half would come out in front, subtract 1 from the exponent. The negative 3 would come out in front, give me plus 15, subtract 1 from the exponent. And derivative of x would just be plus 1. Oh, it looks like Argentina scored again. Sorry. Anybody? Did you see what happened this morning? It's crazy. Brazil scores in extra time. And then 3 minutes left in the extra time, Croatia ties it. Oh, but I didn't see the second goal. I'll have to watch the highlights later. Sorry, that wasn't. So first of all, I'd have to take the time. This has to be changed. This would have to be changed. This would have to be changed. Can you change both at once? Can you see the cube root of x to the 5th is x to the 5/3, but it would be on the bottom. So now it'll be x to the negative 5/3 on the top. Same thing, this will be x to the half on the bottom. So there's our preliminary work. Just manipulating it so that it matches up. Then our derivative would look like 21x squared. Bring the negative 2 out, negative 4x, negative. Bring the half out, negative 5 over 2, x to the negative 1. Bring the negative 5/3 out, negative 5x, negative 8/3, minus 5 over 2. Remember on Wednesday when I said you're going to get really good at subtracting by 1? This was a good subtracting by 1 test. Which I think this one was the hardest one to get. You had negative 5/3. Subtracting 1 would be like subtracting 3 over 3. You're working with negatives. You would get negative 8 over 3. Okay? And I think we're already getting to the point where if someone was looking over your shoulder, okay, first of all, they should know how to do step 1, knowing grade 12 or even grade 11 pre-calculus. But are they good at changing square roots to fractional exponents? Yeah, they'd probably be a little rusty on that. And then you go from this to this, and it looks like you just were making up numbers, right? I should do that once. I should just make up new calculus rules for my students. I just teach a whole lesson where everything is like, yeah, you just do this and this and this. You'd get mad though, wouldn't you? Have a quiz and then tell you, yeah, that was just fake. Teachers have been fired for doing that. But they tend to teach, things like the Holocaust has never happened. You've heard of it, right? That's a whole conspiracy. So then it's sort of like, fired. Should have like trap door boxes in every classroom so that if you do something wrong, the principal can just hit a button and then Long here. Heard you got lost on Inkster.
I did get lost on it.
When you told Jessica you were lost on Inkster, I told Jessica to tell you you're on Inkster. You're not lost. But all good. Okay. Don't worry, I will put what you missed up on video. We got carried away playing with logarithms to start, so. Sometimes we have to be even more creative. Can you see that this one is not in a form that we can use? So if it's not in a form that you can use, you ask yourself, well, what could I do with this one? Could I play around with it? Well, I could multiply it out. If I multiply this out, I'd get 2x squared minus 6x plus 2x minus 4x minus 6. And then you're like, oh, now it is in a form that I can do. So my derivative will be 4x minus 4. You don't have to write the plus 0, but you could if you wanted to. Right? So sometimes we have to take some preliminary steps to get it into a form that we can do. And so far, the only shortcut we know is powers. And we can do any polynomial, which really is a lot of mathematics already. Can you work backwards? If that's the derivative. What would the original equation be? Yeah, 5x to the power 4 plus 5x. Did you pick a favorite number? Plus 21. Nice. Right? Opportunity to add your favorite number to any question.
Do you have to add a number?
You don't have to, because 0 would be right as well.
Can you do it on an exam? Do you just get to pick a random number?
You could. In fact, later on, when we become more formal with working backwards, when we're more formal with working backwards, we'll do this. That is boring. Formal, it's much more fun, right? You could, you're like, I'm finished my test. I finished my test 10 minutes early. You could just keep going. You're gonna add decimals. And at a certain point, with 4 minutes left, I need some extra paper. I have to staple it to my test. That would be fine. I don't know what happened there. I struggled at that moment. But yes, it would be fine if you left no number there as well. Yeah, the formal one is boring, right? Plus c. C for constant could be any number.
So is that what you have to do on the exam?
On the exam, when we get to the more formal ones, in the more formal ones, this same question will look like this. This is calculus for work backwards. But we don't know that notation yet. This is the notation that says work backwards, then the answer would be this. But that's still 2 units away for us. So please ignore that, you never saw it. But I'm giving you an idea of, in mathematics, it's always the case. First of all, you learn how to work forwards. Then you're like, oh, it feels so good. Then like, okay, work backwards. You're like, oh, go back, right? Happened in elementary school. What do you learn? What's the first mathematical operation you learn? Addition. And then what did they make you do? And you hated, you liked addition, but you like subtraction. Oh, this is harder, right? And then you got good at subtraction. You're like, okay, I'm okay. And then what did they introduce?
Multiplication.
Multiplication, right? And you're like, oh, I'm getting this. And then division. You hated division at the beginning because it was harder than working backwards is always a little bit harder. silly. Oh, yes. So we do that all the time. Work forwards, work backwards. All right, I'm going to end this video right